Hello everyone, we are Group 7 from the RMIT Data Structure and Algorithm course, and this is our demonstration sessions for our group project, which is to develop a map application. So in this video, we will give you an overview of the data structures that we implemented, analyze our algorithms and its complexity, and finally demonstrate our system in a computer console with some test cases.
And this is the data structure overview section. Our team had researched and experimented with several different data structures, including KD tree, graph, hash table, and 2D array, but we decided to utilize the WAT-tree data structure to implement in this assessment, as it provides the best performance in running time and acceptable space consumption. So to be more specific, the WAT-tree can efficiently store data points in a two-dimensional space, and each node can have at most 4 child nodes, and each child should store a fixed number of places. Whenever a child node is overloaded, it will split itself into another 4 child nodes and then divide the places data into those nodes. And the right picture indicates how the WAT-tree affect a map. It recursively divides the map into 4 smaller subdivisions at each level. And after that process, you can see right now the map turned into the combination of multiple squares, and this can enhance the searching algorithms and storing data. The next section is algorithm analysis, and I will start with the AskPlay function. We divided this function into 4 steps. First, check whether the given coordinates fall within the map or not. Then we check the validation of the current node's capacity and check whether it's an appropriate node to insert or not. Then we traverse until reaching the appropriate node. And then at this stage, there are 2 scenarios that we need to concern. First, if the chosen node reaches its max capacity, split it to 4 subdivisions and come back to step 2 to find the correct node. Or the current node is valid, so we just insert the new place into that node. And now I will do the visualization for the AskPlay method, starting with step 1. As you can see in the picture, the given place has the coordinates 10,000,001 by 10,000,001. This is clearly out the map. So when we try to add this play into the map, the WAT-tree will throw an illegal argument exception. So in step 3 of the insertion process, the WAT-tree would traverse to find the correct node. And all of the red square you see in the map indicate all the nodes that the WAT-tree would traverse to meet the appropriate node. Following by step 3, after reaching the correct node, a validation is made to confirm that the node has not reached its max capacity. We assume that the node will have the max capacity of 5. And right now you can see it only contains 1. So the WAT-tree would insert a new place. And the red dot you see on the map indicates the current location of the new place in the WAT-tree. And this is the scenario in which appropriate nodes reach its max capacity. So in the picture, the appropriate node had reached 5 places, which is the max capacity that we assume. So the WAT-tree will automatically split the node to insert the new places. And this is the result of splitting that node. The node now have 4 children, and you can see all of its places now rearranged into each children correctly. And the WAT-tree will find the correct node again and add the new place into that node. And the red dot you see indicate the current location of the place in the WAT-tree.
Thanks a lot for the comprehensive explanation. And now we will dive into the algorithm analysis of editing and removing a place on a map using the method edit place and remove place. So technically, these 2 methods share the same concept of traversion inside a quad tree. So the first step in our algorithm is to check whether the current node we are exploring is a leaf node or not. If it's a leaf node, then the next step will be iterating through the array list layer inside the node. And if it's not, we will recursively call the appropriate method on the child node that contains the coordinates. And finally, once the place is found, we'll perform the update by changing the service or remove the place by shifting the remaining places inside the nodes. So to illustrate these methods, we will present a visualization of traversing inside the quad tree. So on the map on the right side, the red dot is the coordinate that we need to traverse to. And as you can see, at first we will identify whether the current node is a leaf. In this diagram, it is not yet a leaf node, so we will recursively call the method again until the current node is a leaf node that has the boundaries which contain the coordinates. And lastly, once we found the leaf node, we will iterate through the array list inside the node to find the desired coordinates, which is the red dot right here.
So the next section is about the search play algorithm. On the right hand side, there is a code of the search play method in the map2d class. And this method will include 4 main steps. Step 1 is to create a boundary rectangle based on the user position and the distance that they are willing to walk. And in step 2, the system will traverse through the quad tree to find all the suitable places and add those places to the result array. Then it will sort the array using the merge sort algorithm and return the nearest k places from the result array. Now I will show you the visualizations of the search play algorithm step by step. So first, the system creates the searching boundary rectangle based on the user position and the distance that they are willing to walk, which is the green area on the map. After that, the system will traverse through the quad tree to find the nodes that intersect with the searching boundary, which are represented as the red rectangles on the map. And then it will collect all the suitable places that are inside the searching boundary rectangle and host the searching services. Those places are represented as the yellow points on the map. So while collecting all the suitable places, the system will also calculate the distance between those places and the user position to prepare for the next steps. So after searching for suitable places, the system will sort the result array based on the distance of the place to the user position using the merge sort algorithm. So assuming that the result array has 5 elements, the merge sort algorithm will divide the array into smaller subarrays, sort each subarray independently, and then merge those sorted subarrays to produce the final sorted result. This sorting algorithm ensures that places are closer to user position will appear first in the result. So when the sorting algorithm process is completed, the system will create a new array to store the first k places from the sorted playlist and return that array as a result.
So about the complexity of the algorithms, I will provide an overview of the time complexities for essential operations in the map2d data structure. Utilizing a quad tree, we will briefly touch on the complexities of adding, editing, removing, and searching places. About the general complexities for add, edit, and remove place operations. They typically operate with a complexity of big O of log n, which is efficient for balanced tree and typical use cases. For search place operations, usually runs with a complexity of big O of log n plus m, leveraging the quad tree's spatial querying capabilities for fast searching and sorting. There are some special cases about the worst cases, like for add place, the complexity can increase to big O of n in areas with high density or frequent deep split. Edit and remove place may escalate to big O of n plus m or big O of n respectively in the scenarios involving unbalanced tree or densely packed node. Such play might reach big O of n log n if extensive data sets closely match the search criteria, necessitating comprehensive sorting.
So now moving on to the demonstration of our map2d data structure implementation. So we have prepared here a client code in the main class. So this is the main class to test some basic functions of the map2d. So I will run the main class for an example. As you can see, the result printed out on the console. So it successfully insert 100 million places in around 10 seconds, and the memory it used and the runtime of other operations, as well as we test the search operations by input the user location and the distance they're willing to walk and the rest the services that they are searching for, and we print out the result in a table format for better readability. So as you can see here, so because we want to make sure that our code work correctly, so we utilize a mapping project in our Java project so that we can implement some test cases for the operations to make sure that they run correctly. Here is the main test file. We have several test cases, and now I will run the test file. So as it says here, we have 16 test cases in total. So we're gonna go through it. So first of all is the add place, normal add place. So we add a place within the bounds of the biggest map, and it successfully add the place right on the from input here, as you can see. And we also test, try to add a place that is out of bounds. Like for example, we use the coordinate of 11 million. Then the expected exceptions would be the illegal argument exceptions, and we get that. And for the edit, we have 3 test cases. First is try to edit an existing place, and it's successful here. And now we try to edit a non-existing place right here, and the edit status must return 4 and the size must return 0 because there are no place that we are looking for. And we also test for the edit propagations, because we want to make sure that the edit operations only work with the place that we want to edit, but not the place that next to or have the coordinators close to it. So it successfully edit the place without affecting the near places, as you can see from the output of the test. Moving on to remove. So we also have 3 test cases for the remove. First is remove an existing place. So it's returned successfully as usual. And we also try to remove a non-existing place, and the removal status return 4 as expected. And lastly is the remove propagations. So again, we want to make sure that our remove operations only work with the place that we want, but not the place that is close to it. And it's passed the test like here. And for the search, we have several search tests. Like basic search over here, we have some input, and it returns the 3 places in a list format like this. And we have a boundary search, which is we include a custom boundary with a work distance of 100 units, and return nothing because there are no match result in that such small boundary. And we also test with several other boundary like 100 by 100. With other service, it returns 1 place. We also test with 1,000 boundary and 10,000 by 10,000 boundary, and it returns all information here. We also do empty search, which means that we search for a service that no places offer. So it has to be returned 0, like the result has to return nothing. And again, we want to have a search for a place that is out of map, and it should return 0 as well. And lastly, we want to test the performance of the search. Must be lower than 200 milliseconds. So that is 16 of the basic test cases that we test the map 2D. We also have some insertion tests, which is we try to insert a batch of places from 10 places to even 100 million places. And I will run the test. So it takes a while for the test to run because as 100 million places, it took around 7 seconds to maximum of about 10 seconds. So we have it printed out in a table so that we can do some benchmark. So that's all for our demonstration. Thank you for listening, and see you next time.